Hello viewers, welcome to Big Boy Physics, and today I'll be discussing you with a problem from kinematics, that is from USAPHO 2023. Well, actually someone in my comment section actually posted a question. You may see it in one of my videos comment section. That is, this is the whole problem. I'm not exactly reading the problem. Well, I'm not here to solve his problem, but I am here to discuss another similar problem. Actually, his problem probably maybe someone has given it to him. It's actually taken from USA PSO 2023. So what he has posted is only few part of this question. That is only the part 2 of A. That is part A sub part 2. But in this question, I'll be discussing about part A sub part 1, 2, and also part B, as well as part C also. So hope your wish will get fulfilled by discussing this problem. So let's get started. The question says that in this problem we consider a small ball bouncing back and forth between 2 points. In all parts below, the acceleration due to gravity is g and collisions are perfectly elastic. Air resistance is negligible. The impact points are at same height, and the diagram is not to scale. Then you have to answer the following subparts. First is, consider a ball bouncing between two cylindrical planes which make an angle theta less than 90 degree to horizontal. The ball has speed v naught at the impact points, which is separated by distance capital D. First question, you have to tell me the possible values of theta so that the ball can bounce back and forth along the same path or the same trajectory. For convenience, I am deleting the picture consisting his post. So yeah. Now, first question says about that we have to basically trace the path. Right. Now, observe one thing. If the ball has to trace the path, and given that the collisions are elastic, so what should we say? That coefficient of restitution is 1. And if the ball begins from point A to and hits the point B, then point B, the trajectory makes 90 degree with respect to the incline, and at point A also it will make 90 degree with respect to incline. Hope you get it. So basically, there's no restriction in theta. Only restriction is in the trajectory. And if you observe, then this angle that is with respect to vertical will be theta. So v naught square sine 2 into 90 minus theta by g is equals to d. That is the third equation of projectile. What you say about the range? Okay. Then you will get v naught is equals to root gd by sine 2 theta. Yeah, one thing for sure we can comment is that this should be greater than equal to root g, right? So basically we'll get a lower bound of v naught to in this problem. So first part of mine is done. Now coming to second part. Second part says that a ball can also take one trajectory while traveling to the right and a separate trajectory while traveling backwards. Let phi denote the angle between the path at the impact points. Then you have to comment on how theta and phi should vary for this motion to be possible, given that phi is non-zero. Right? Now, what is the key observation in second part? Well, the key observation is that suppose we have a ball hitting the incline at an oblique angle, then if it's an elastic collision, then it will have angle theta, and that is angle of reflection and angle of incidence will be same. Basically, it will deflect by same angle, right? Now, this is the first observation. Second observation is that the range, if we write range as a function of theta as r theta, then r theta is equals to r pi by 2 minus theta or 90 minus theta, for as per your convenience. I'm writing in radians. So basically what it says that range of angles in which are complementary, better to say, the angles which are complementary provides the same range. So this is the key point here. Now that means that if my if this is my trajectory 1 and this is trajectory 2, then the trajectory along the bisector will make an angle 45 degree with respect to horizontal, and this will make an equal angle with respect to the bisector, that is a line with making 45 degree with respect to horizontal. Okay, that's no big deal. So we can say one thing, that with respect to horizontal, incline must make 45 degree. Hence, if the projectile starts here making an angle phi, better it's since they have already used phi, let me write it as phi by 2, because they have used phi as the difference of the angle between the paths. So similarly, there will be another such possible trajectory with phi by 2 like this, and they will meet at the same point, and this motion continues. Now coming back to what will be the possible values of phi and theta. Well, v naught square sine 45 minus phi by 2 ka twice by g is equals to d. From here you'll get v naught is equals to root vd, root gd by cos phi, and that's the answer to the second part. Well, one thing I can say, that this will be greater than equal to root gd. We get the lower bound. Okay, so the viewer who has commented must have got his answer from the second part, because he asked only that much. Well, in this question, I'll be solving the part B also and part C also. So, part B says that suppose the ball bounces within a hemispherical well of radius of curvature r. As in part A, it takes two alternative distinct paths of time periods of time of flights t1 and t2, where t2 not equal to t1. Then you have to tell me the possible values of r in terms of t1 and t2. By using the previous result, I can say that the hemispherical ball is something like this. Then it will the oscillation or the motion will take place from this point such that this will make 45 degree, right? So basically my in D in this case will be R root 2, right? One thing I can say, that V naught cos pi by 4 minus phi by 2, that is for the one of the path, into T1 is equals to R root 2. Similarly, V naught sin pi by 4 plus phi by 2 minus G T2 by 2 is equals to 0, because we are considering a half of the maximum time, that is basically when that, the projectile goes from here to here, then it will take time is equals to t2 by 2. Next thing what we'll say is that v naught cos pi by 4 minus phi by 2 is equals to gt2 by 2. So I will get r is equals to, basically cancelling all the terms and finding the values, basically dividing with these two, you will get r is equals to g t1 t2 by 2 root 2. So that's the answer. Well, the part B can be done in various ways. You can use various kinds of equation, writing all these such possible values, writing the time of flights, writing the possible ranges, and finding all the respective values. You can do whatever you want, but this one was one of the method. Part B, you can also give alternative method in the comment section also, but trying to keep it precise, only giving one method at a time. Okay. Now coming to part C. Part C is also similar. Part C says that in this case, we have to take in a well of sinusoidal shape y as a function of x minus L sine 2x by L, and the ball takes two distinct paths with time of flight t1 and t2 not equal to t1. The horizontal distance between the impact points are less than pi l. Find all the possible values of L in terms of T1 and T2. Now part C is actually connected to part B. The methodology is same, but we need to understand how can we visualize the paths. Okay. For part C, I am keeping it as a homework, but I'll be giving you the answers, and I'll give you one small hint that there will be two cases in this problem. So I'll be explaining you the cases. If you want to try now, you can try now, or if you can't, then you can use the help of my hints I'll be giving. So the hints are something like this: that if this is my graph, will be something like this. There will be two modes. In first modes, the same thing, that pi by 4 angle at pi by 4 angle at the oscillation occurs. This will be first mode. Then the second mode will be something like this. Here the angle will be 45 degree. Here also the angle will be 45 degrees, and the oscillation occurs somewhat like this. Okay. So there are two modes in this case as I have shown. Hope you understood it. So that's all for today. Thank you and have a nice day.